the load_s instruction, also known as load string. It has a few forms. The first one is load_sb, where b stands for byte. This instruction loads a byte from location in memory ESI and then copies it into AL. And then immediately ESI is advanced by 1 byte according to the direction flag. If the direction flag is 0, ESI is increased by 1. If the direction flag is 1, ESI is decreased by 1. The next instruction, load_SW, where W stands for word. This time we load a word from the location in memory ESI, and then we copy it into the AX register. Then immediately ESI is advanced 2 bytes according to the direction flag. The third form of this instruction is load_SD, where D stands for dword. In this form, we load 4 bytes from the location in memory pointed by ESI and copy it into EAX. Then immediately ESI is advanced 4 bytes according to the direction flag. I just want to note that this instruction is some kind of complement for the STOS instruction. The STOS instruction takes the value of AL or AX or EAX and stores it into the location pointed by EDI. I remind you that EDI stands for destination index. However, this form reads the string. It goes to the location in memory pointed by ESI and then reads the value and stores it into AL, AX or EAX. So the two instructions, STOS and load_s, are somehow dual. Let's look at an example for the load_s instruction. We begin with a declaration of array, which is called myArray, stands for myArray. Every element in this array is a dword, and we have a total of rlen dwords, which means that we have a total of 4 times rlen bytes. We are going to sum all the dwords in this array. And by the way, we assume that rlen is some constant that was defined earlier in the source code. Let's take a look at this code that we have here. We assume that this array, my array, was initialized somehow before. Maybe it was given from the user in some way. Maybe we read some input and stored it inside the array. But now, at this point, we want to sum all the dwords in the array and get the result. Let's try to run this code and see how it works. As usual, we have this view of the memory. This time we look at my array. And we watch those 3 registers, EDX, EAX, ECX, at all times to see the way that they change. We also assume that the direction flag is 0. We are not going to touch it here, but I just wanted to make sure that you see how this piece of code assumes that the direction flag is 0. So let's begin. First we load ESI to be the beginning of my array. I draw it like this. ESI points to the first cell in the array. Next we move rlen into ECX. So ECX is going to count the amount of iterations of this loop that we can see here. And we got the value 3 inside ECX. Here we assume that rlen is of size 3. We can also see that my array is of size 12 bytes, which corresponds to the value 3 of ECX, or the value 3 of rlen, because 3 times 4 is 12. Next we zero EDX. EDX is going to be the sum of all the entries in the array. it is going to be the sum of all the D words. So initially, we want it to be 0. Now we are inside the loop. In every iteration, we are going to do those two instructions. First, load SD, which is going to load one D word from the array. And next, add EDX EAX, which is going to take the D word that we have just loaded and add it into EDX, which is the total sum. Let's see how it works. The load SD instruction is at this point going to load this D word. I'll remind you that Intel x86 architecture is little endian based, which means that this D word is actually 1. We are just seeing it reversed in memory. So we got 1 inside EAX, and we can also see that ESI has advanced 4 bytes to the right. That is because the direction flag is 0. Next we add what we got in EAX into EDX. And we get to the next iteration of the loop. We can see that ECX is going to decrease now. In the next iteration, again we read this D word, which is pointed by ESI, into EAX, and we add EAX into EDX. So we get 4. Finally, we read the last D word, which is now pointed by ESI, into EAX, and then we add EAX into EDX. The result is 9. And the loop is going to finish now. Note that in the end, ESI points to a virtual next D word. It might be some other thing. Maybe I have in memory something not related to this array at this point. But ESI always points to the next D word. This is an important edge case to look at. The next instruction we are going to talk about is MoveS. This instruction stands for move data from string to string. As usual, it has few forms. The first one is MoveSB, where B stands for byte. This instruction basically takes 1 byte from the address pointed by ESI and copies it into the memory pointed by EDI. This is a 1 byte copy. Then immediately ESI and EDI are advanced 1 byte, and this is according to the direction flag. If the direction flag is 0, ESI and EDI are increased by 1. And if the direction flag is 1, then ESI and EDI are decreased by 1 byte. The next form is MoveSW, where W stands for word. Here we read 2 bytes from the memory pointed by ESI and store those 2 bytes into the memory pointed by EDI. Then immediately ESI and EDI are advanced 2 bytes according to the direction flag. Finally, we have the third form, MoveSD. MoveSD does about the same, just with 4 bytes. It reads 4 bytes from the location pointed by ESI and stores those 4 bytes into the location pointed by EDI. Then immediately, ESI and EDI are advanced 4 bytes. They are increased or decreased according to the direction flag. Some notes about the MoveS instruction. It is pretty amazing that MoveS can access 2 memory locations at the same time. So far, we haven't seen any instruction that can do it. For example, the simple move instruction cannot move directly memory to memory. As you probably remember, it has this limitation. But MoveS is a pretty special instruction. It has this special feature, the ability to access 2 memory locations at the same time. In fact, it reads one memory and writes to another memory location at the same time. In fact, it first reads from one memory location and then copies the result into the destination memory location. Another thing to note is that ESI stands for source and EDI stands for destination. Maybe from the first two instructions that we have seen, the STOS and load S instructions, you haven't noticed it. But now it is a good time to notice that ESI is always the source and EDI is always the destination. It is some kind of a convention in the x86 instruction set. If you remember, the STOS instruction stores data into the location pointed by EDI, which is the destination. And I also remind you that the load S instruction loads memory from the memory pointed by the ESI register. Finally, move S is like some kind of combination of those two instructions. It reads from ESI and stores data into EDI. I think this is a good way to remember what those three instructions do. The three instructions STOS, load S, and move S, which really complement each other. ESI and EDI are both incremented or decremented according to the direction flag. Just like we had for the STOS and load S instruction, this is also true for the move S instruction. The direction flag determines the direction in which ESI and EDI advance. MoveS is very useful for copying data, as we are going to see now. Let's take a look at an example of the MoveS instruction. An example of copying data. We have two arrays, one called source array and one dest array. Both of those arrays are arrays of bytes, which means that every element is a byte. This is just how we imagine those two arrays. And we have this constant rlen, which we assume that it was defined earlier in the code. We are going to see that in this example we choose this constant to be 6, but it could be anything. You may also assume that source array and dest array have been declared in different data sections. Maybe one of them was in the data section and one of them in the BSS section. I just wanted you to see them one next to each other, so I wrote it that way. I also assume that the dest array is initialized with zeros and that the source array somehow contains meaningful data. Here we can see that it is uninitialized, but maybe some earlier code has initialized it to be some important value or maybe some input from the user. So you can assume that source array has some important input from the user. Let's take a look at the following code. We are going to inspect it instruction by instruction. As we said before, we assume that rlen is of size 6 bytes. And this is how we imagine the contents of source array and of dest array. Let us assume that source array contains those nice numbers. 1, 1, 2, 2, 3, 3, 4, 4, and so on. Let's begin with the first instruction. First we load source array into ESI, which means that ESI is going to point to the first cell. Next, EDI is going to point to the first cell of dest array. The third instruction, which we do before we enter the loop, is about choosing the amount of iterations. We move rlen into ECX, which means that now ECX contains 6, which is the amount of iterations that we are going to see in this loop. We have this label copy byte, and this loop is very short. It contains only one real instruction. The other instruction is just about jumping to this label, to copy byte. ECX is going to be decreased in every iteration because of the loop instruction. Basically, the only real job done inside this loop is this MoveSB instruction. I think that it is pretty amazing that you can just do one instruction in every iteration and still get some meaningful work being done. Let's see what happens. We begin with this MoveSB instruction. This instruction is going to copy the contents of this cell pointed by ESI, which is the source, into this cell pointed by EDI, which is the destination. As expected, 1, 1 was copied here, and then immediately ESI and EDI were advanced by 1 byte. We assume here that the direction flag equals 0. So ESI and EDI were both increased and not decreased. Next we move on to the next iteration. So ECX is decreased by 1. And again we copy from the source to the destination. The end is always interesting, at least in my opinion. I really care about the edge cases of the loops. I think they say a lot about the loop itself. Let's see what happens in the end. This is going to be the last copy iteration, where we copy from the source cell 66 to the destination, where EDI points. In some kind of an interesting way, ESI and EDI are increased. This is pretty much as expected, but now they point to some location that is not related to those arrays. Maybe there is some other memory here. And finally, the loop ends. This was a simple example of copying data from one location to another. One location pointed by ESI is the source, and the destination location is pointed by EDI. Summary of what we have seen. We have learned about the three instructions: STOS, which is store string, load_s, which is load string, and move_s, which is about moving data from one string to another string. And we have also seen that those three instructions are somehow dual. Mostly, move_s is like some kind of combination of STOS and load_s. It should be easy to remember that ESI is the source and EDI is the destination. This applies to all of those three instructions. We also learned about the direction flag. The direction flag determines the direction to which ESI or EDI are advanced after each of those instructions. I remind you that those three instructions change ESI or EDI. If the direction flag is 0, we expect ESI or EDI, or maybe both, to be increased. If the direction flag is 1, we expect ESI, EDI, or both to decrease. This is what I wanted to tell you about STOS, load_s, and move_s. See you next time.